Hello everyone, I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to explain another part of IR spectroscopy, that is known as theory of IR spectroscopy. It is Hooke's law, which is related with vibrational frequency of a functional group. To explain the Hooke's law or vibrational frequency, again we discuss ball and spring model of a molecule. A molecule is similar to a model in which two balls are connected by the spring. Here we can consider two atoms of different masses M1 and M2 are connected by a weightless spring. These two atoms are considered as two balls of different weights. This spring is always in a state of continuous vibration. When we apply energy, the vibration of a particular amplitude of a particular vibration can be increased. If we want to calculate the energy for this vibration or frequency for this vibration, Hooke's law is used. Hooke's law, according to Hooke's law, frequency, it is known as frequency is inversely proportional to mass and directly proportional to bond strength. Here, in terms of wave number, it is 1 upon 2 pi c under root k upon mu. Here, one thing I want to tell that we are writing wave number nu bar, but it is usually say vibrational frequency. Actually, it is universally accepted myth in the literature also. The wave number unit used in IR is known as vibrational frequency, and Hooke's law, which gives the relation of wave number with different parameters, is Hooke's equation. Wave number is equal to 1 upon 2 pi c under root k upon mu, where k is the force constant. The unit of force constant is Newton per meter or dyne per second. And mu is the reduced mass, which is related with the masses of two atoms. M1 mu is equal to M1 M2 divided by M1 plus M2. If we solve this quantity, 1, 2, value of pi is 22 by 7 and c is the velocity of light, then the final value will be 130.3 under root k upon mu. That means the vibrational frequency or the energy required for the vibration of a particular bond depends on the force constant and reduced mass. Vibrational frequency depends upon two parameters: bond strength, it is related with the K, force constant, and reduced mass, which is mu. Here you can see vibrational frequency is directly proportional to under root K and inversely proportional to under root 1 upon mu. Larger the value of K, force constant is related with the bond strength. Suppose the value of force constant for single bond is 1 into 10 to the power 5 Newton per meter. Then for double bond, this value will be double, and for triple bond, it will be triple. As the bond strength increases, the value of force constant increases and more energy is required for the vibration of a particular bond. That's why vibrational frequency value will be increases. If the bond connected with the lighter atoms, then the vibrational frequency will be higher, and if the reduced mass of the atoms will be higher, then it can easily be vibrated, and the value of vibrational frequency will be lower. Less energy will be required for such vibration where the two atoms of heavy masses are connected by a covalent bond. Here you can see the same different bonds within the same atoms. Carbon-carbon triple bond, carbon-carbon double bond, and carbon-carbon single bond. The value of reduced mass is same for all the three conditions. C1 and C2 is the same. M1 and M2 value is the same for carbon. But for carbon triple bond is very strong. Here is triple bond strength will be higher. Larger the value will be K, and the vibrational frequency will be maximum. In case of carbon-carbon double bond requires less energy as compared to triple bond. So double bond requires less energy for the vibration as compared to triple bond, and more energy as compared to carbon-carbon single bond. That means for the vibration of carbon-carbon double bond, 1650 centimeter inverse shows the absorption. Another example shows the effect of reduced mass on the vibrational frequency. Larger atoms, larger the value of reduced mass, lower the value of the vibrational frequency. CH, carbon and hydrogen single bond, carbon-carbon single bond, carbon-oxygen single bond. Out of these three cases, the atomic masses of carbon and oxygen is maximum, and carbon and hydrogen is minimum. When reduced mass is lower, it shows absorption at higher frequency or higher wave number or higher energy will be absorbed. It shows absorption as 3000 centimeter inverse. For carbon-carbon single bond, more reduced mass as compared to carbon-hydrogen. Vibrational frequency will be lower, 1200 centimeter inverse. Similarly, carbon-oxygen bond has maximum reduced mass, so it shows absorption at the minimum value. That means the value of vibrational frequency or the energy required for the vibration of a bond depends on two factors: strength of the bond and masses of the atoms connected by the covalent bond. Since molecule as a ball and molecule represents a ball and a spring model, it means the covalent bond present in a molecule in between the atoms are in the constant vibration. When we apply radiation or energy, the amplitude of a particular vibration may increase. That means by the absorbing of energy, amplitude of a particular vibration may increase. This results in the change in internuclear distance and vibrational transition. Here you can see in the graph, different vibrational levels are present in a single electronic energy level. After applying electromagnetic radiations or IR radiations, vibrational transitions are possible, and depending upon the energy of the radiation, V0 to V1 or V0 to V2 transitions may be possible. From the ground state vibrational level, molecule may excite to the first state vibrational level or second state vibrational level. This is known as vibrational transition. Transition, which is in between the V0 to V1, when molecule excited from V0 state to V1 state, then this type of transition is known as fundamental transition, and band obtained in the IR spectrum because of this transition is known as fundamental band. Energy required for the fundamental transition will be equal to the energy of the final level minus energy of the initial level. That means energy of energy of first vibrational level minus energy of zero vibrational level. So the total energy required for fundamental transition is h nu. When the transition involved from V0 to V2 state, this type of transition is known as overtone transition, and the band obtained by this transition is known as overtone band. Energy required for this transition is equal to energy of the second vibrational level minus energy of the zero vibrational level, and the total energy change during that transition from V0 to V2 state is equal to 2h nu. That means overtone transitions appears as double frequency as compared to fundamental transition. One more thing, since fundamental transition requires less energy, these transitions are possible at room temperature. These are the most probable transition, whereas overtone transitions require more energy. These transitions generally not very much probable at the room temperature. So the intensity of the overtone bands generally very low as compared to fundamental transition, but overtone appears at the double frequency as compared to fundamental vibrations. Theoretical number of fundamental bands. What is the meaning of theoretical number of fundamental bands? One band represents one type of vibration of a bond connecting the two atoms. In case of polyatomic molecule, different bonds are connected by different atoms are connected by different bonds, and every atom can undergo all types of vibration: symmetric, antisymmetric, banding, in plane banding, and out of the plane banding. All the vibrations may possible in the single bond that connects the two atoms. So that means in case of polyatomic molecule, when multiple bonds are present, theoretical number of fundamental bands can give an idea about the number of bands observed in the IR spectrum. Theoretical number of fundamental bands for linear molecule we can calculate by the equation 3n minus 5. It is related with the 3 degrees of freedoms present in the molecule: translational degree of freedom, vibrational degree of freedom, and rotational degree of freedom. Vibrational degree of freedom will be equal to the theoretical number of fundamental vibration, and which is for the linear molecule is equal to 3n minus 5, where n is the number of atoms in a molecule. For non-linear molecule, it is 3n minus 6. Carbon dioxide. Carbon dioxide is a linear molecule, so we can apply the equation 3n minus 5. According to this equation, the number of atoms is 3. 4 fundamental bands are possible in the carbon dioxide molecule. This is the theoretical value of fundamental bands. Second example is of benzene. Benzene is the example of non-linear molecule. It has 12 atoms. The value of n is 12. So the number of fundamental bands for benzene is 30. That means in case of benzene, 30 fundamental bands will appear in the IR spectrum. But generally, theoretical number of fundamental vibrations or theoretical number of fundamental bands are not observed in the IR spectrum. Sometimes it may be less or sometimes it may be high. What may be the reasons? First reason, the fundamental vibration may fall outside the region of investigation. The main working IR region is from 2.5 micron to 15 micron, or we can say from 4000 centimeter inverse to 666 centimeter inverse. If any of the fundamental vibration is not shows absorption in this region, then it not appear in the spectrum. Sometimes the fundamental vibrations are too weak and they cannot be recorded. Sometimes different fundamental vibrations require more or less equal energy. They are very close to each other and they can overlap. One more thing that is most important in the IR spectroscopy. If any of the vibration which do not involve any change in the dipole moment during the vibration, it will not appear in the IR spectrum. Other than this, sometimes, other than theoretical number of fundamental vibrations, some additional bands like combination, difference, and overtone bands may appear, which increases the number of bands observed. Main thing, only those vibrations will be IR active which involve change in fluctuating dipole moment of bond during the vibration. To generate the dipole moment, the polarity of the atoms must be different. Here, if we come to the conclusion about the similarity between the theoretical number of fundamental bands and actually observed fundamental bands. First, we are taking the example of carbon dioxide. In carbon dioxide molecule, 4 types of fundamental vibrations are possible according to theory. Now we discussed each vibration. First is the symmetric vibration. Symmetric vibration, that means both the oxygen atoms with respect to carbon may close to each other or going far apart from the carbon. That means with respect to carbon, the oxygen is more electronegative, but when the bond is vibrating, the change in bond length is the similar in the positive side and negative side. That means the change in dipole moment will be 0. When this type of vibration does not produce any change in the dipole moment, this vibration will be IR inactive. Since in both the sides, the difference in bond length is the same. Suppose here is -5 micron, here is +5. So minus and plus will be cancelled and the total change in the dipole moment will be 0. So symmetric vibration is IR inactive. Antisymmetric vibration. In antisymmetric vibration, polarity is the same. From one side, the carbon-oxygen bond length decreases and from the other side, carbon-oxygen bond length increases. In this condition, this vibration must have some change in the fluctuating dipole moment. So this type of transition will record in the IR spectrum and it will be known as IR active vibration. Another, banding vibration. In carbon dioxide, out of plane banding is possible. At one time, both the oxygen atoms going above from the plane and another time going below from the plane. Energy required for both the transitions, both the vibrations is similar. That's why it is considered as the degenerate vibrations and considered as one vibration because they appear at the same energy. So theoretical number of fundamental bands calculated for the carbon dioxide is 4, but actually in IR only 2 bands are produced by the carbon dioxide molecule. but one by the antisymmetric vibration and another by the bending vibration. That is degenerate. That means two vibrations appear at the same energy. Another example of nonlinear water molecule. Theoretically, water molecule has three possible degree of freedom and three number of fundamental bands can be possible. One from antisymmetric, another from symmetric, and third for bending. For water molecule, all three theoretical fundamental bands are IR active. Bonds which do not absorb IR radiations. Since only those vibrations will be recorded which involve change in fluctuating dipole moment. For fluctuating dipole moment, there must is the change in the polarity of the atoms connected by the bond. If the atoms of the same polarity connected by the bond during the vibration, there will be the no change in the polarity, so the dipole moment will be zero and the molecule will not show any absorption in IR region. First such type of molecules are symmetric diatomic molecule. Same atoms are connected by the bond. Upon vibration, there is no change in the dipole moment, so they will not absorb IR radiation. Symmetrically substituted alkene and alkyne. When on the double bond and on the triple bond, same substituents are present, then there is no change in the dipole moment and these vibrations are also considered as IR inactive vibrations. Which group shows a strong absorption in the IR region? Only those vibrations will be IR active which involve change in fluctuating dipole moment. The value of dipole moment depends on the polarity of the atoms connected by the bond. The electronegativity difference or the polarity difference, as the higher the polarity of the bond will be higher and the dipole change in the dipole moment will be higher. And that particular group shows maximum absorption in the IR region. For example, carbonyl group. In carbonyl group, oxygen is electronegative. It has tendency to withdraw the electron. That's why it has partial negative charge and carbon has partial positive charge. This bond is polar. Because of the polarity, when this bond vibrates, there is the change in the fluctuating dipole moment and it will shows maximum absorption in the IR region and shows sharp peak in the IR spectrum. Similarly, for OH and carbon oxygen bond. In both the cases, oxygen is more electronegative with respect to hydrogen and with respect to carbon. These bonds also produce change in dipole moment during the vibrations. So they also shows strong absorption in the IR region. The whole IR region from 4000 to 400 centimeter inverse is divided into two regions. First is the group frequency region. It is from 4000 to 1500 centimeter inverse and most of the functional groups or most of the functional group including stretching vibrations generally absorb in this region. Approximate frequency of many functional groups can be calculated from atomic mass, cis and force constants by using Hooke's law equation. Positions changes a little with neighboring atoms, but often in same in general region. That means, for example, if the carbonyl group shows absorption nearby 1700 centimeter inverse. In case of ketones, the R may be CH3, C2H5, C3H7 or C6H5. The value of C double bond O group absorption slightly changes with the change in neighboring atoms of alkyl group. Group frequency region serves as a good initial guide to compound identity. That means from group frequency region, we can have an idea about the functional group present in the molecule. Second region of IR is the fingerprint region. This region is from 1300 to 500 centimeter inverse. As the name indicates, fingerprint, as fingerprint of every human being is individual or unique. In the same way, this fingerprint region is always unique for a single molecule. When the functional groups are same, but the fingerprint region will be different. So fingerprint region is the region of most single bond signals. Many have similar frequencies, so affect each other and give pattern characteristics of overall skeletal structure of a compound. By fingerprint region, exact interpretation of this region of spectra can be possible because of the complexity. And this complexity is related with the uniqueness of the spectrum. By IR spectrum, these are the following information can be obtained. IR is most useful in providing information about the presence or absence of a specific functional group. IR can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. When the spectrum is completely overlapped at the fingerprint region, that shows the two spectrums are of identical compounds. IR does not provide detailed information or proof of molecular formula. It only provides information about the functional group present in the molecule. Therefore, it is very limited in scope and must be used in conjunction with other techniques to provide a more complete picture of the molecular structure. Thank you.